Hello again, this is Radioisotopes Part 2. In the last video we looked at nucleus of copper, and I'm not going to draw all the protons again, so I'm denoting these red circles as a proton and the grey ones as a neutron. So we have neutrons in the nucleus here as well. And in the last video we fired a neutron into the nucleus, and neutrons of course have no charge, so they don't experience the electrostatic repulsion that protons do, because protons have positive charge. This time we're going to fire a proton at the nucleus, and I've got an example here also where we make nitrogen 13. So alchemists tried to do this for many hundreds of years. They wanted to change the makeup of the nucleus of an atom, turning lead into gold and things like that, but never could. They tried this with various chemical reactions, and of course the energies needed to get that proton to bind with this nucleus are really high because of that electrostatic repulsion. And the closer the proton gets, the greater force that it experiences. So a little force here, and then the force gets bigger as it gets closer, and that's by the inverse square law, of course. So closer it gets, the bigger it gets. This happens all the time. It happens in our star, the sun. Temperatures are high enough that the kinetic energies of the protons, or the helium, the hydrogen nuclei in the sun, fuse together. No problems. Those sorts of kinetic energies are available there, but they're difficult to get to happen here on Earth. Luckily, a proton also has charge, because we can accelerate it in a cyclotron, and I haven't done a video on cyclotrons, but basically we have a circular path for the proton, and it's accelerated via an electric field, and it's directed circular via a magnetic field. And this was first created in I think the 1930s, around there sometime, and they're inexpensive enough now that they can be part of the facilities at various hospitals around Australia. And so we can make radioisotopes by firing positive nuclei at other nuclei in cyclotrons. So here's what they sometimes do. This is the nuclear reaction that occurs. That's a hydrogen nucleus, of course. A mass number of 1 and an atomic number of 1. This is oxygen, atomic number of 8, mass number of 16. We end up with a nitrogen and a helium nucleus, or the alpha particle. Now this is the guy that we accelerate. We accelerate that in a cyclotron, or hospitals accelerate that in cyclotrons. They fire it, they direct it towards an oxygen nucleus, and the reaction that takes place, the nuclear reaction that takes place is the products are nitrogen-13, which is an isotope. Okay, so that's our radioisotope there. And a helium nucleus. And this radioisotope can be used in medical imaging, just like the copper 64 in the last video. And this one's much more short-lived, though. It has a half-life of around 10 minutes, thereabouts. And so this has to be made on site. Wherever the patient is, the cyclotron needs to be. So I'll just label that too. Wherever, yeah. So because as soon as you take this this nitrogen-13 out of the cyclotron, it's not going to last very long, and so it needs to go directly into the patient. The imaging needs to be done, and then of course the tracer just dissipates in the body and becomes harmless in a very short amount of time, which is of course good for the patient. Now this proton here, hydrogen, it's a proton, needs to be accelerated. Now it has to be accelerated to a kinetic energy of 5.55 MeV, and that's of course 5.55 times 10 to the 6 electron volts, and we do that in the cyclotron. And I'm running out of space here, so I'll finish this off in the next video. It'll be called Radioisotopes Part 3.